China just built the fastest robots on Earth. And we're not talking about industrial arms bolted to factory floors. We're talking about humanoid robots that can sprint, jump, and move with agility that seemed impossible just months ago. These machines are rewriting the rules of bipedal locomotion. You're about to see 8 robots that prove speed and agility in humanoid form have finally arrived. Let's start with the absolute fastest humanoid robot ever built, H1 by Unitree Robotics. Picture a humanoid robot running at 12 miles per hour. Not walking, not shuffling, full-on running, with both feet leaving the ground between strides. That's the H1, and it's currently the fastest humanoid robot on the planet. The breakthrough is in the actuators. Each joint delivers 360 Newton-meters of peak torque while weighing just over 2 pounds. That power-to-weight ratio generates the explosive force needed for running. But raw power means nothing without control. The H1 uses sensor fusion combining inertial measurement units, joint encoders, and foot pressure sensors, feeding into a balance controller that adjusts 1,000 times per second. When your foot leaves the ground at 12 miles per hour, you have milliseconds to predict landing. The onboard computer processes terrain data and adjusts joint angles mid-stride. Here's what makes it work. The robot weighs 103 pounds with a carbon fiber frame. Every pound adds inertia the actuators must overcome. The battery pack sits low in the torso, keeping the center of gravity stable during high-speed movement. The gait algorithm generates movement in real time based on terrain and velocity, not pre-programmed patterns. That's why it transitions from walking to running seamlessly. The next robot proved you don't need to sprint to push boundaries. Star 1 by Robot Era. 8 miles per hour doesn't sound as dramatic as 12. But here's the thing. The Star 1 can maintain that speed for extended periods without overheating or losing stability. That's an entirely different engineering problem. Sustained jogging creates thermal challenges that sprinting avoids. The actuators generate massive heat during continuous operation. Star 1 solves this with liquid cooling channels running through each joint motor. The coolant circulates through a radiator system in the torso, dissipating heat before it degrades performance. Without this, the motors would overheat in under 2 minutes. The energy efficiency is what sets it apart. Star 1 uses a gait optimization algorithm that minimizes energy waste with every step. Instead of lifting the foot high off the ground, it calculates the minimum clearance needed based on terrain sensors. Less vertical movement means less energy burned. The result is a robot that can jog for over an hour on a single battery charge. But the real test happened in the Gobi Desert. Outdoor terrain introduces variables no lab can replicate. Loose sand, rocks, uneven ground. Star 1's foot pressure sensors detect surface compliance in real time. When it steps on soft sand, the control system immediately adjusts joint stiffness to prevent the foot from sinking. On hard rock, it reduces impact force to protect the actuators. This next robot came from the same company but pushed the technology even further. Era L7 by Robot Era. Robot Era took everything they learned from Star 1 and rebuilt it from scratch. The L7 represents the next generation of their locomotion technology, and the improvements are significant. The actuators got a complete redesign. Higher torque density means more power in a smaller package. Each joint now delivers 400 Newton-meters while weighing less than the Star 1's motors. That extra torque translates directly into faster acceleration and sharper direction changes. But the biggest upgrade is in the control system. The L7 runs a predictive algorithm that anticipates terrain changes before the foot touches down. It uses stereo cameras to build a 3-dimensional map of the ground ahead, planning foot placement 3 steps in advance. When it approaches an obstacle, the system has already calculated the optimal trajectory to clear it. The sensor array expanded too. More IMUs distributed throughout the body provide finer control over balance. The L7 can recover from disturbances that would topple earlier designs. Push it mid-stride and it adjusts within milliseconds, redistributing weight and repositioning limbs to stay upright. What really sets it apart is the movement range. The hip and ankle joints have increased degrees of freedom, allowing more natural motion patterns. It can sidestep, walk backwards, and pivot, without the rigid mechanical movements of older humanoids. LimX Oli by LimX Dynamics. LimX Dynamics built the Oli to solve a problem most humanoid robots ignore: moving fast while carrying heavy loads. Most speed-focused humanoids sacrifice payload capacity for agility. The Oli does both. The robot stands 5 feet 9 inches tall and can carry up to 33 pounds while maintaining full mobility. That payload sits in an integrated cargo compartment in the torso, keeping the center of gravity stable. The actuators are oversized to handle the additional weight without compromising speed or balance. Here's the engineering breakthrough: variable stiffness actuators that adapt based on load. When carrying weight, the joints automatically increase resistance to prevent sagging or instability. Under light loads, they soften for more natural movement. The control system adjusts stiffness in real time as the robot moves. The Oli uses a quad-core processor running parallel control loops. One handles balance and locomotion. Another manages manipulation tasks. A third processes sensor data. The fourth coordinates everything, ensuring smooth integration between walking and object handling. That computational separation prevents lag when the robot switches tasks. The leg design is wider than typical humanoids, providing a more stable base. Wider stance means better lateral stability when carrying loads. The trade-off is slightly reduced maximum speed, but the Oli still walks at nearly 4 miles per hour while fully loaded. This next robot obsessed over full-body coordination. Agibot X by Agibot. Agibot built the X for industrial environments where speed alone isn't enough. The robot needs to manipulate objects while moving, and do it fast. That requires coordination between locomotion and arm control most humanoids can't achieve. The arms have 7 degrees of freedom, each with actuators capable of 20-kilogram payload at full extension. The arm control system and leg control system operate independently, yet synchronously. The robot walks while its arms perform complex manipulation without interfering with balance. The torso houses a 6-axis force-torque sensor, detecting any imbalance from arm movement. When the arms extend to one side, the control system automatically shifts the legs to compensate faster than the imbalance can destabilize the robot. It walks while moving heavy objects side to side without breaking stride. Multimodal locomotion adds another layer. The X walks forward, backward, sidesteps, and rotates in place with different gait patterns optimized for each movement. Switching between modes is seamless because the control algorithm preloads the next pattern while executing the current one. Joint response time is under 5 milliseconds, enabling fluid coordination between walking and manipulation. The next robot focused purely on movement range and flexibility. Kuavo by Leju Robotics. Kuavo is built around one principle: maximum degrees of freedom equals maximum agility. This robot has 52 independent degrees of freedom spread across its entire body. That's more articulation than most humanoids even attempt. The hip joints alone have 6 degrees of freedom, enabling rotation, extension, and lateral movement most humanoids can't replicate. Combined with 3 degrees of freedom in each ankle, the legs can position the foot at almost any angle relative to the body. That flexibility allows stepping over obstacles, climbing varying stair heights, and balancing on tilted surfaces. The control system runs inverse kinematics calculations at over 500 Hz, solving for optimal joint angles in real time. Each of those 52 joints needs independent commands coordinated with every other joint. The processor handles this fast enough to adjust mid-motion without lag. The arms have 7 degrees of freedom, each creating a workspace that covers nearly the entire area around the robot. It can reach behind itself, above its head, and down to ground level without moving its feet. That range makes manipulation tasks far more practical than limited motion designs. This next platform took a completely different approach, with open architecture. Tiangong by Beijing Humanoid Robot Innovation Center. Tiangong is an open-source humanoid platform, and that changes everything. Instead of one company refining the design, hundreds of engineers worldwide contribute improvements. The result is rapid iteration on speed and agility features. The modular joint design is the key. Each actuator unit is standardized and swappable. Researchers can test new motor designs or control algorithms by replacing individual joints without rebuilding the entire robot. That modularity accelerates development dramatically. The walking speed sits around 3.5 miles per hour. What matters is the sensor integration architecture. The system accepts inputs from any compatible sensor, whether cameras, LiDAR, or force torque sensors. Developers add new sensing capabilities by simply plugging in hardware and uploading drivers. The control system runs on open-source software, allowing anyone to modify movement algorithms. One team optimized gait for energy efficiency, another focused on rough terrain stability. A third improved disturbance response time. All those improvements merge back into the main platform. Every breakthrough benefits the entire design. The final robot on this list proves that reliable precision still has a place. Walker S by UB Tech. The Walker S isn't trying to break speed records. It's engineered for precision and reliability. Walking speed maxes out around 2 miles per hour, but that's deliberate. The focus is consistent, repeatable movement that doesn't fail. Each joint uses harmonic drive gearing for near zero backlash. When the motor stops, the joint stops exactly where commanded, with no drift. Precision is within 0.5 millimeters across thousands of cycles. That matters for navigating tight spaces and handling delicate objects. The balance system uses 6 IMUs distributed throughout the body, providing redundant stability data. If one sensor fails, the others compensate automatically. The control algorithm cross-references all sensors to detect anomalies and ignore faulty data. That redundancy prevents falls from sensor glitches. Energy efficiency is exceptional. The Walker S operates for over 8 hours on a single charge because it's not fighting to maintain high speeds. The gate optimization minimizes energy waste with smooth, controlled steps. Low power draw means smaller batteries, which reduces weight, which further improves efficiency. From 12 miles per hour sprinting to 2 miles per hour precision walking, these 8 robots represent the complete spectrum of humanoid locomotion. The actuators got lighter and more powerful. The sensors got faster. The control systems learned to process terrain and adjust in milliseconds. Humanoid robots aren't just walking anymore. They're running, adapting, and moving with capability that seemed impossible just years ago.